All right, we're going to talk about inscribed angles and polygons. So first, to understand what an inscribed angle is. An inscribed angle is where the angle lies on the circle. So if we say we have a point here, excuse me, that isn't, well, point there, point there, and point there. The vertex of the angle lies on the circle. So if we were to call this, say, angle ABC, we'd say that angle ABC is inscribed in our circle. Okay, the intercepted arc of this angle is arc BC, because arc BC is subtended by angle ABC. So subtend means when an endpoint, when an endpoint of a chord or angle actually, or arc, lie on the sides of an inscribed angle. Okay, let's fix that up there. When the endpoint of a chord or arc lie on the sides of an inscribed angle, that means subtend there. And the only reason I bring up that term is because it's brought up in our textbook there. So we could say arc AC, or excuse me, chord AC subtends angle B. You could also say arc AC subtends angle A, or angle B, excuse me. All right. So it cuts that angle there. All right. The measure of an inscribed angle. The measure of an inscribed angle theorem. So the measure of an inscribed angle is half the measure of its intercepted arc. All right. And so we have this, let's give it a different inscribed angle here. Let's use a different color. So let's say I have the inscribed angle, and we'll call it this time WXY. All right. The measure of angle WXY is going to be 1/2 of the measure of arc WY. So for instance, if this arc WY was, say, 120 degrees, the measure of angle WXY would be half of that, or 60 degrees. Okay? Let's take a look at the next one here. If two inscribed angles of a circle intercept the same arc, well, let's go ahead and do that real quick. So let's say I have, there's an inscribed angle. Let's draw that again. There's an inscribed angle there. And let's label that A, B, C. Okay, and then let's go ahead and draw another inscribed angle. This time, go right there, and we'll call this D. We'll notice both angle ABC and angle ADC intercept the same arc, arc AC. Okay. Therefore, since they intercept the same arc, these two angles must be congruent. So for instance, if arc AC was, say, 100, let's just go with 100 degrees, that would mean angle ABC is 50 degrees. And since ADC intercepts that same 100 degrees, this would also, ADC would also have to be 50 degrees. So what we know is that 1/2 the measure of arc AC is equal to the measure of arc ABC, which is equal to the measure of arc ADC. So if two inscribed angles of a circle intercept the same arc, then those angles must be congruent. They have to be the same. All right. Let's go ahead and try play some of these. Find the inner or indicated measure. So the measure of arc WV. So WV is right here. Well, notice WV is intercepted by WXV. Okay, so this arc subtends that angle. Okay, it's at the end of that angle. So what we know is that twice the measure of WXV is this arc. So 2 times 42 is equal to 84. All right, so the measure of arc WV is 84 degrees. All right, well, let's go ahead and switch over to measure of angle V. So we're now here at this measure, angle V. Well, angle V is right here. And notice, angle V is subtended by arc XW. Well, note that arc WV and arc XW make up a semicircle. So therefore, 84 plus this angle, or this arc, has to add up to 180. Okay, so the measure of arc WX plus the measure of arc WV equals 180 degrees because it's a semicircle. And we already know WV is 84. Okay, so we can substitute that in for arc WV. That means we just need to subtract that 84 from 180 to find the measure of arc WX. So the measure of arc WX is 180 minus 84, also known as 96. Okay, well, if this is 96, notice that's not what I'm necessarily looking for. I'm looking for this angle right here. Well, half of 96 is half the measure of arc WX. So we have 1/2 of 96, which is equal to 48. And that's one way to do it. All right, that's 48 degrees. The other way to do it would be to figure out the measure of W first. Well, the measure of angle W, notice angle W, and I know my picture is getting a little messy here, but notice angle W is subtended by arc XV. Okay, arc XV subtends angle W. And notice arc XV is 180 degrees. It's a semicircle, which means angle W is 90 degrees. So if we know angle W is 90 degrees, we could have figured out measure of angle V because 42 and V would have to add up to 90 as well. Okay, so a couple ways to do that. All right, let's go ahead and try another one here. Find the measure of FP. So I'm going to look at this. I note that arc FP subtends angle FEP, F to E to P. So that's a 35. So twice 35 is FP. So that's 2 times the measure of angle FEP. And FEP is 35, so that's 2 times 35, which gives me 70 degrees. Okay, so FP is 70 degrees. Okay, so this arc. All right, well, measure of angle FDP. So let's switch up our colors here. We'll go F to D to P. Well, notice that angle is subtended also by 70 degrees. So it's 1/2 of arc FP. And we know FP is 70. So 1/2 of 70 is 35 degrees. The other way, and some of you may have figured that out right away, the other way to do it is to say, well, angle FDP and angle FEP are subtended by the same arc, therefore they have to be congruent. That was one of the theorems. They're both the same measure. They're both 35. Okay, well, arc PD. Arc PD is that other arc. Oops, switch that up again here. It's rests here. And notice I say the rest because it completes our semicircle. So if this is 70, 70 plus PD, measure of PD, is equal to 180. So the measure of PD, arc PD, must be 110 degrees. All right. Well, let's go ahead and inscribed polygon. So an inscribed polygon is a polygon with all vertices on the circle. So let's say, oops, that's a bad word. Let's go ahead and put a vertex. I'm going to put a couple here. Okay. There we go. I'm going to put a vertices and then I'm going to connect them. Vertices means I'm just putting some points. I'll try to actually connect the points there. Okay. All right. I have a, oops, 1, 2, 3, 4, 5, 6 inscribed hexagon right there. Okay. A circle that contains an inscribed polygon is called a circumscribed circle. Okay, so inscribed polygon, all vertices on this or lie on the circle. Okay. I've tried to allude to this throughout the lesson here, but an inscribed right angle theorem. If a right triangle is inscribed in a circle, so let's say I have a right triangle here. So I have a 90-degree angle. I've done my best. Sometimes trying to draw really slow doesn't help your picture. That didn't help either. Let me try this again. Oh, it's a little better. Okay. I promise I'm going to get it there. For crying out loud. Well, we're going to leave it at that. Okay. An inscribed triangle. Or inscribed right triangle. Wow. You know what? I think I just have to turn my screen there. It's amazing when you turn your computer screen. Okay. An inscribed triangle, or right triangle, so let's make this a right angle here. If a right triangle is inscribed in a circle, then the diameter, then the blank is the diameter of the circle, then the hypotenuse. Okay, and I'll explain why here. If I've done my best to go through the center of the circle there, we'll call that the center. We'll fix that up that is really bad. Let's fix this picture. Sorry, getting type A about this. So let's say I have this circle, and I have a diameter going through the center here. Okay, and I have another point out here somewhere, and I connect it to there, and to there, oops, to there, for crying out loud, to there. Boy, this is a comedy of errors here. There we go. Okay, this has to be a right angle. And in fact, no matter, I really hesitate to do this, but no matter how I draw my diameter, so let's say I put my diameter there, I put another point right there, and there, oops, to there, that has to be a right angle. Or, once again, I know I keep doing this over and over, and maybe belaboring the point, but put that there, put a point there, go from there to there to there. Notice each time I get what looks like a right triangle. And it has to be, right? Because if this angle right here, let's label this A, B, B, and C. So if angle ABC, or ACB, excuse me, is subtended by arc BA here, arc BA or AB is 180 degrees. Okay? Notice our angle is subtended by that arc. All right? So the hypotenuse is a chord. It's the diameter of the circle. This has to be a right angle, always. Okay? Because this angle C is always subtended by a semicircle. Okay? No matter how you draw it. So once again, if I had to erase that whole mess there, I put my center and I draw in a diameter, no matter how I do it, if I put the point there, there's my right angle. Why? Because this arc from here to here, that's A, B, and C, arc AB is 180 degrees. It subtends angle C, therefore it has to be a right angle. It'll always be the case, no matter how you try to draw that. Okay? So conversely, if one side of an inscribed triangle is the diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is the right angle. Okay? So in other words, if you have one side that's a diameter, then the angle opposite it's going to be that right angle. Inscribed quadrilateral theorem. Okay, well, let's go ahead and switch some colors up here. Okay, a quadrilateral can be inscribed in a circle. Okay, well, let's go ahead and do that. So 1, 2, 3, and 4. I'm going to try not to make what looks like a square or rectangle. I'm just going to do there we go. Okay, it can be inscribed in a circle if and only if its opposite angles are, well, you know what, I'm going to switch some colors up here. Let me switch some colors on my opposite angles. So let's do this. All right. So if we were to call this, say, angle A, actually let's switch, let's go Q, R, S, T. So angle Q. Notice angle Q is subtended by arc RT. Okay, now I don't know what arc RT measures, and I don't know what the measure of angle Q is. But what I do know is if I look at the angle opposite, angle S, it is subtended by arc TQS. And notice when I combine arc TQS, this arc, and this arc, that completes this entire circle. Okay, I know that this angle is going to be half of this arc, and this angle is going to be half of this arc. Those two arcs put together grab me a grand total of a full circle, or 360 degrees. So combining these two angles would have to be half of that, 360, which would be 180. So a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. They will always, opposite angles of a quadrilateral will always add up to 180 degrees. Same thing would happen with T and R. Notice R is cut by this top arc, T is cut by the bottom arc. Makes 360. Okay, so let's go ahead and find some values of the variable here. So I'll apply this. Notice that 3x plus 6 is angle C, and angle C is subtended by a semicircle or by a diameter there. Therefore, this arc is 180 degrees. Okay, so 3x plus 6 would have to equal 90. It's half of 180. If that's the case, 3x equals 84, and 1x is 28. You can check it. 3 times 28 is 90. Half of 180 is 90. All right, take a look at another one here. Find the values of each variable. Well, notice I have angle G, and that is opposite of angle A, right? So I have angle G there. I have angle A here. Well, this is a quadrilateral. GHAF is a quadrilateral, so these two angles must add up to 360. Okay, so 21x minus 2 plus 38x plus 5. Usually you'd see those in parentheses, just showing that those are two different angles. Add up to 180 degrees. Sorry, if I just said they add up to 360, they add up to 180, right? Opposite angles of a quadrilateral add up to 180. So 21x and 3x, 24x. Negative 2 and 5 is positive 3. Subtract 3, so 24x is equal to 177. Okay, you know what? I think I missed a, yeah, I did. That's not 3x, that is 38x. So for those of you like, whoa, what happened to the 8? I forgot it. Okay, so 21 and 38 is 59. All right, 59x, holy moly, that could have been a catastrophe. So 59x equals 177. 59 goes into 177 3 times. Okay, so I substitute 3 in and add the 2 up, I get 180 there. All right, one last problem. This one is a little tougher. It has to do with systems of equations. Okay, so notice I have angle L, and, well, first I have a quadrilateral. And angle L plus the measure of angle N would have to add up to 180. Okay, so what I could do is say, well, that's 7x plus 1 plus 2y plus 74 equals 180 degrees. I could then move on and say, well, I know that angle V and angle M would also have to add up to 180. So the measure of angle V plus the measure of angle M equals 180 as well. Okay, so V is 2y plus 100. M, 6x minus 10. Now you want to solve this system of linear equations. Now, there are multiple ways to solve systems. Okay, I personally look at this and I see right away that this equation, even before simplifying it, equals 180, and this equation equals 180. So if two different, this expression and this expression equal 180. So if two different expressions equal the same number, then those two expressions must be equal. So that would mean that 7x plus 1 plus 2y plus 74 has to be equal to 2y plus 100 plus 6x minus 10. Now, sometimes this is helpful, sometimes it's not. The reason why I can do this here is because I recognize right away that they both have two y's and they're going to be on opposite sides. So when I look to simplify this, you know, if I were to take and go, well, 7x and 2y, can't combine those, but 1 and 74, and then 2y and 6x, and 100 minus 10. And I look at this and I go, I'm going to collect all my y's on one side. Well, when I subtract these two y's over, they cancel these two y's. So I'm now left with 7x plus 75 equals 6x plus 90. Subtract 6x, I get x plus 75 equals 90. Move the 75 over, x is equal to 15. And if x is 15, I can substitute that in. Right? If I say, well, I know that I can either substitute it in here, here, or here. I can substitute in multiple places. But if I were to maybe use this top equation, okay, well, 7x plus 1 plus 2y plus 74 has to equal 180. And so if I put that 15 in, if I substitute it in for x, that's going to give me 7 15s plus 1 plus 2y plus 74 equals 180. Okay, well, 7 15s, that's 105, plus 1 is 106, plus another 74. Okay, well, that's 180 plus 2y equals 180. Well, subtract 180 over, you get 2y equals 0. So 1y is, well, that's 0. It looks like x is 15 and y is 0. Now, anytime I get 0 as a number, I double check it, but that is actually the case here. If you substitute y in, 2 times 0 is 74, or 2 times 0 plus 74 is 74. That would make this angle 74. And substitute 15 in, 7 times 15 is 105, plus 1 is 106. Well, 106 plus 74 is 180. It works out. If you do it on this side, on both these sides, this would give you 100. And then 6 times 15, that's 90 minus 10 is 80. That works out as well. So my solution is x is 15, y is 0. If you need help solving systems, you really need to be talking to your math teacher on that. Okay, if you can't remember how to do that from algebra, there's substitution, elimination, and graphing. You're probably going to use substitution or elimination on that. Okay? Well, that's all I got for you. Good lucky.